Hi and welcome. This time around I am going to be investigating the press plates that came with the Harbor Freight 20-pound press. A lot of people in the comments have mentioned that in presses of old that these plates would fail catastrophically, and my guess is they used to make them out of cast iron. When I drilled the holes for the pins on this, they did not seem to be cast iron, but what I'm going to do is I'm going to test the theory and see if I can actually make one of these fail catastrophically. I am first going to make an adapter plate to fit on the outside of this adjustable ram, and then I am going to make a conical adapter piece to fit on the end, and I'm going to push in the worst way possible at one single point. That'll give you maximum force per square inch. This is a pretty dangerous thing I'm going to do, and I am going to try and do as safely as I possibly can, but just as a warning, don't try this at home, and I am definitely doing something risky that probably should not be tried. If you watched my earlier videos on the Harbor Freight 20-ton press mods, one of the things I did was I took the ram out of the 20-ton jack that came with it and repurposed it to make an adjustable ram for the new press. And I made it removable so that if I wanted to use a different ram I could, if I didn't want the adjustability, but also that makes it easy to take out for measurements. So my first design iteration, I was going to create a cup that basically fit over this, that just had a set screw with a conical point that caught the bottom. But I've got a simpler design. I still have a bunch of these quarter 20 set screws that have a little nylon bushing on the end, and I can just come in and press on the side. And so that'll make for a simpler design. And since all of the force is going to be wanting to compress this adapter that I'm putting on here onto the arbor itself, it doesn't need to be strong. It just needs to have friction to hold it in place so that it doesn't fall off between operations. So I've got these guys. I'm going to get started on making this part. Also, it's just going to have a little 3/4 nub sticking out of the top, a cylindrical portion that the adapter parts can fit on top of. I might take that down to 1/2 inch. Again, it doesn't need to be strong because all its job is to center it up. All the force should hold the plate against this, as long as we don't have any lateral forces like you push off center and it makes the arbor want to move, to bend at an angle, to flex out of the way. So it needs to be strong enough to avoid that sort of operation, but most of the force should be axial. So let's get started. First step is going to be cut off 1.75 or actually 2 inches of this 4140 bar here. It's 2 1/4 inch diameter, and in the old days I would have had to cut this with a hacksaw because the portaband just couldn't cut it. So we're going to see how this guy performs. This thing so far, this Baxter Verticut, has been an outstanding saw and one of my best purchases ever. So let's give it a shot, see what happens. I will say it's cutting faster than I expected. Very impressive. So I do use some wax lubricant on the blade, and I refresh it a couple times during the cut, just to give myself some better blade life, because that's what I believe it's going to do. I am not certain. I've just been told and read about it. So looks like we have a minute or two left, and we're going to be through this piece. That's really impressive. This is a 3/4 inch, and I think it's a 10/6 variable pitch blade, meaning some of the teeth are 10 per inch and some of the teeth are 6 per inch, but it's cutting very smoothly. I get a sense of economy of what this saw does for me. Every time I get a cut like this, when I buy a large bar, it would cost $10 per cut from my supplier to make these pieces. On top of that, they don't even stock 4140, it's special order only, so it would be really problematic, and you pay a premium for it. So I got this piece on eBay for a deal, and now the fact that I can cut it myself saves me a boatload of money. So if I cut this into like 20 of these pieces, I just saved $200. This saw is going to pay for itself pretty quickly. Anyways, let's move on. Next we're going to take it to the lathe. We're going to face both sides and get going. We're going to take first cut 50 thousandths depth of cut, and we're going to go in at 7 thousandths of revolution at 680 RPM. Let's see how it works. Not breaking a chip. Second shot, same RPM, 14 thousandths of revolution, 50 thousandths depth of cut. Still not breaking a chip. Ah, there we go. Starting. So I want the tip of my drill bit at the surface here, and I want the tip to only go in no more than ½ an inch. So to set that up, I take this 15 thousandths of an inch shim stock and I set the drill bit very lightly against it and zero my DRO, and then go in another 15 thousandths to compensate for the thickness, and we should be right at the surface. If you're interested about in my DRO, I made that in a different project, so feel free to check it out. With carbide end mill. This will give me a nice starting point to work from. By the way, if you're curious, I was holding this end mill in a 5C collet that mates up with the Morse taper on the tailstock here. It's great for getting a flat bottom hole, and it tends to cut straight without wandering, especially since it's carbide, so there's not a lot of flex. Now we're boring, and I sped it up. Feed rate's kind of slow, but we are at 680 RPM, 2.2 thousandths of revolution. I'll have to break the chip because the chip's not breaking on its own. Alright. That was 100 thousandths pass. And as you can see from the chips here, they're not turning blue, so we're not pushing it too hard. They're actually a beautiful shiny color on one side and sort of brown on the other. You've got to be really careful with these chips because these chips are seriously sharp. So probably should handle them with the pliers, but wanted to show you what they look like. So I'm going to do several more passes because we've got to get to 1.77 inches. And I'll do another couple passes and bring you back. Try and take the last 77 thousandths all in one bite. The finish I'm getting taking big bites is amazing, so I hope I can keep it up. I was doing 100 thousandths depth of cut. This will be 77 thousandths. Alright, we should be close to our final dimension. I'm going to give it a measure and then we'll flatten the bottom. .777, which is right exactly where I wanted it. Now it is warm, so it might be actually a little bit small, but we're going to go with this. Now we're going to turn this, go in ½ an inch, or go in 3/4 of an inch, turn it to a ½ inch diameter. The center ½ inch diameter is simply to locate the part and provide some surface for friction for the set screw to push on, just hold it in place. 150 thousandths depth of cut, 7 thousandths of revolution. Actually bogs things down just a little bit. You can hear it. Still not breaking a chip. So we might want to try this smaller depth of cut and larger feed rate. But again, we're only going in 3/4 of an inch, so it's going to make it really tough to stop on time, but we'll try it. 300 RPM, 14 thousandths of revolution, and 50 thousandths depth of cut. Still not breaking chips. inside dimension done. Facing next. Those are some hot chips. A little bit of chatter there. Probably should have gone slower RPMs. I was going really high RPMs with a really slow feed rate, and that was giving me a better finish longitudinally, but didn't seem like they worked as well radially. I probably should have gone slower. So, a little bit of chatter here made not an ideal surface finish. Didn't take a big enough bite. That's a little bit of sanding, not a great surface finish. This is a much better surface finish. This was 100,000ths depth of cut, and it seems like that's what 4140 really likes, aggressive depths of cut. So we got to take this over to the mill and drill and tap a 1/4-20 in the side here, and then we need to make the conical piece to be our presser point, our presser foot, if you want to call it. That's going to see if we can break those plates, or do they just bend. So no sooner do I finish this guy than I change my mind. So I got the set screw in with the nylon foot on it to hold this part on the hydraulic press. But I've changed my mind about this 3/4 by 3/4 proud piece here. Alignment, what do you call it? Alignment nose or something like that. Anyways, I'm going to reduce this down to 1/2 inch diameter by 1/2 inch depth, because all it is for alignment, and I've thought of another way that I'm actually going to try and mount, hold the press pieces on, whatever you call those specific pieces, the multiple adapters I'm going to have on this. What that allowed me to do is use smaller diameter stock than, say, like the 2.25 inch stock that this is. There is no real reason for this, because no force is actually applied to this piece. If I was going to use this, I would have made the hole 3/4 of an inch by about 0.8 deep, so that there's no chance that it would press here. I want the pressure to be on the outside portion of it. I mean, you could try and design it so that everything would be equal, but I don't think that's really necessary, especially when using 4140. So I'm going to chuck this guy back up in the lathe, and we're going to make adjustments to the length and diameter of this part. All right, so here we are with the finished nose sticking out 1/2 inch by 1/2 inch. And I said it was going to be done, but actually I forgot. I've got to put a couple grooves in here, because the way I'm going to hold the press pieces on is with O-rings. So I'm going to recess some O-rings on here so that they're just proud, and then when anything I stick on there, the O-rings will hold them in place until I press, you know, the part. But they don't actually have to support anything other than just the weight of the press piece that I made. Okay, so next up we're going to create 2 grooves, and I don't have a round bottom, although I suppose I could grind that carbide so that it has a round profile, but it's just to hold a couple O-rings, and I don't think that's going to be important. They're not sealing anything in, they're just to apply a little pressure. So I think the solution will be, I'm going to go in a total of 1/8 off the diameter, or 62.5 thousandths radially, and we'll see how that works out. So if you happen to catch one of my other videos, I made this set of mold and die so that I could squeeze copper into the shape of protective covers for my other 4-jaw chuck, the one that came with this lathe. This was this Bison was an acquisition I got on eBay for a great price. Couldn't pass it up. Always wanted a really high quality 4-jaw chuck. Anyways, so this whole system was based on 1/2 inch arbor, and so you'll notice that fits nice and snugly on there just with the O-rings, and that'll hold it in place long enough to press your part, and this shouldn't fall off. I still didn't get the O-ring exactly right. I think I still need a little more practice. Plus the O-rings I got were some inexpensive ones, and I don't think they were dimensionally very close to what they said they'd be. So in any case, next step, we're going to make our conical press foot, or press piece, whatever they're actually called. Just going to drill, center drill first. Oh, this stuff's pretty hard. Alright, so I finished the adapter that will fit on the adjustable ram to allow me to put other presser pieces on it. Let's call them noses or feet. I don't know what you actually call them. And that's what this is here. This fits on there. And now I'm interested what diameter I want here. And the way I figure that out is how much pressure am I interested in applying to the press plates to see if they'll break. So let's go over and take a look at some math. It won't be too much. So here's what we have to work with. I have a jack that'll put out 20 tons of force or 40,000 pounds of force. If I want 40,000 pounds per square inch, then I need to apply 40,000 pounds over a square inch. So area of a circle, which is the shape of that foot, is pi r squared. And so if I start with an area of 1 square inch, then I can solve for r and figure out what radius I need to get 1 square inch of radius. Well, if I come down here, 1 inch squared is equal to pi r squared, and I'm interested in this radius. Rearranging this formula is not hard, but if you don't know how, I've got the answer down here, but you basically first divide both sides by pi, which is 1 over pi, and then take the square root of both sides to make the r separate. And now you've got the radius equal to the square root of the area over pi. So working that out, I get pi 0.564 inch radius or 1.128 inch diameter presser foot. So we're going to go and reduce this presser foot that I've made to be 1.128 so we can apply 40,000 psi. Now, if I wanted to apply a whole lot more force, okay, I'm stuck with the 40,000 pounds, that's fixed. But if I reduce the area, that will cause the force to be much greater. So right now it's 40,000 pounds in 1 square inch. Imagine if I were to make the area a 1/4 square inch. That would make this 4 times as much in psi, which would be 160,000 psi. Now, I'm starting to get close to the strength of the material itself, which means it's likely to deform or fail. Also note that based on what I looked up, for most common metals, the tensile strength and the compressive force of failure are very close to the same number. So you can look up tensile strength numbers and find that as a relatively accurate measure of what it's going to fail under compressive force, which is what we're doing here. So next up, we're going to take this back to the lathe and we're going to turn this down to the 1 and change inches, so in a conical kind of shape, and I'll make it so that I can keep reducing it in diameter if I want to apply more force to the press feet and see what point they fail, if they ever do fail catastrophically. Now, if they're a ductile material and they're not really hard, then they will deform first. And that would be interesting in and of itself. That would mean that you're not worried about a catastrophic failure, most likely. If they're hard and brittle, then they could fail catastrophically. So let's proceed and find out what the answers are. So I use the tip point to be the center. I'll know I'm centered on this guy. And it looks about right. So let's start simple. I have a piece of 1/8 inch aluminum here, and let's see what 40,000 psi does to that. By the way, these press plates are now dividing the load, and I have 2 pieces of 1 inch thick cold rolled that are also spreading the force out, so I don't expect anything like a failure. This material, remember I said is 4340, and this is 4140. So let's just go to it. We'll just go to the full force of the 20-ton jack and see what happens to the aluminum under that much force. Okay, we are under 20 tons of force, and not much seems to have happened. I'll be surprised if it didn't leave a mark. I actually thought it would do more. Now you can see we unloaded the whole assembly here. It did press it into the surface a little bit, so there is an indentation. But I'm kind of thinking that we may need more force, because what I was looking for is it to punch into the aluminum a bit, and then I'd feel more confident that we could cause this to fail if it's brittle. So although people say it fails as is, but Why don't we do that? Let's go and make this much smaller diameter, get us a higher pressure capability. Alright, so now we've taken the point down to half the diameter, which means 4 times the force because of the square relationship, pi r squared. So half times 2 is a quarter, and so that actually makes the force 4 times because now we have 1/4 the area. So this will be 160,000 pounds per square inch on some aluminum. I'm both wearing some safety glasses and standing off to the side. I wish I had a way to measure force, but I do not. All right. So, as you can see, it deformed the aluminum, which is what I wanted, and almost punched a hole clean through it, 1/8 inch stock. Looking closely at the cold rolled, it punched right through the oxide layer on the outside and just chipped it right off, or maybe it's stuck on the aluminum. You can see some of the aluminum material in the cold rolled steel. So next time around, we're going to be trying all of this force on not splitting the force between 2 plates, but all of the force on one single plate, which is going to set it up for catastrophe if it's headed there. Plus, of course, I drilled the holes, which people have shared their concerns about. So we will find out and see what happens. All right, so here we go. I put an indicator on there to see what kind of deflection we're going to get, and if it comes back or if it's deflection such that it can't recover from it. Let's make it touch. There we go. Already some deflection. There's 10 thousandths. Okay, I think we are currently at the full 160,000 psi on that point, and that guy has not broken yet, and I kind of suspect it won't. But if we want to help it out, to see if it's fragile, we can give it to see if it's got a stress riser or something that will shatter. So one down and no breakage. Gotta say, I'm a little disappointed, to be honest. Here's number 2. Maybe we got lucky with number 1, so we're going to try number 2, and I'm going to put the full 40,000 pounds of pressure or 160,000 psi force onto this, and we'll see if we can make it break. Okay. Comes up really quickly because this thing does not move a lot. Okay, I think that's about it. Again, no fracture. This project was multifaceted in that I got more out of it than just testing to see if the press plates would be damaged. I got a new ram attachment piece and one nose, or whatever you're calling them, to put on the end of it. I can make more in the future. I can apply a fair amount of force, and you can see this is 1/8 inch aluminum. I was able to make it deform around the nose of this. The press plates each have a fairly deep, maybe 20 thousandths deep depression in them where the nose pressed in. The nose itself didn't get damaged, so that's kind of cool. There'll be more in the future, but there was no loss here because, number one, I feel comfortable that these guys aren't going to shatter on me during usage, which is a big problem, at least based on the capacity of this jack that I've got in there, this hydraulic jack. I mean, perhaps hydraulic jack never put out 20,000 pounds of force, but that's neither here nor there, because at the most I could get out of it, it couldn't crack these. All it did was make a depression. Also, the the fact that it made a depression suggests to me that it's not hardened or a hard material and brittle, but rather it's soft because it deformed. So that's a good sign too. So I hope you find it useful, and thanks for watching. Hope to see you next time.